In this lesson, we are going to actually solve optimization problems. Up to this point in the last couple of lessons, we've just been learning about parts of optimization problems, about the feasible regions and coming up with the constraints and the objective function. Today we are going to put it all together and actually solve optimization problems. Linear programming is a mathematical technique used to determine which solutions in the feasible region result in the optimal solutions of the objective function. So in our first example, we have a toy company manufactures two types of toy vehicles, racing cars and sport utility vehicles. Because the supply of materials is limited, no more than 40 racing cars and 60 sport utility vehicles can be made each day. However, the company can make 70 or more vehicles in total each day. It costs $8 to make a racing car and $12 to make a sport utility vehicle. There are many possible combinations of racing cars and sport utility vehicles that could be made. The company wants to know what combinations will result in the minimum and maximum costs and what those costs will be. So we need to find which combination will result in a minimum and maximum production cost. The first thing we need to do is we need to assign variables. Now you can choose whatever variable you want. We are going to use S to represent the sport utility. And we are going to use R to represent the racing cars, so the number of racing cars. So that's the first thing you want to do, is to identify your variables. Now, are there any restrictions on these? Is this discrete data, continuous data, whole numbers, integers, real numbers? In this case, they are both whole numbers. You cannot produce a negative amount. You cannot produce a decimal amount, but you can have zero and you can have positive values. So these are from the elements of whole numbers. So we know that our graph is going to be simply in the first quadrant. The next thing we want to do is look at our constraints. So we have to look at what it tells us in the question. Well, we know that these have to be greater than or equal to 0 because they are whole numbers. We also know that they can only make up to 40 racing cars. So racing cars has to be less than or equal to 40. And the sport utility have to be less than or equal to 60. The other thing that we know is they can make 70 or more. So if we make both of these together, racing cars plus sport utility, they can make 70 or more, so greater than or equal to 70. So there are our constraints. These are the inequalities we are going to have to graph and find the vertices in the feasible region for. We also have our total production cost. This is going to allow us to find our maximum and minimum. So this is the objective function that we are going to look for. We're going to let capital C represent the total cost. Now the total cost is $12 per sport utility plus $8 per racing car. So this is the objective function, and that's what we want to find the maximum and minimum values for. So now that we've set up our constraints, we can graph this information. Now we know we're dealing with discrete data, so we're going to be stippling. We need to assign our axes. Let one of them be sport utility and one of them be racing. And it really does not matter which you choose, but just make sure you label it so that you know what it is we are plotting. So we know that we're going to be in the first quadrant, so we've set our axes on 0, 0. We know that our sport utility has to be less than or equal to 60. So let's say we go up here by 5s. So we'd have 10 here, 20, 30, 40, 50, 60. So we are going to have our line and it's a stippled region. And we need to determine if we are stippling to the left or to the right of this. S is less than 60. So less than 60 would be to the left. Confirm that by using a test point. If you put 0 into the S, 0 is less than or equal to 60. So we are going to be shading left, or stippling left. And I'm not going to stipple the entire region at this point in time, but that's where we are going to be stippling the S less than or equal to 60. R less than or equal to 40. Let's do the same thing with our racing cars. So here is our R equals 40. Now we need to determine if we are going to stipple above or below this line. Because R is less than 40, the values that are less than would be below. Check using a test point. If you put 0 into that, you will get 0 is less than or equal to 40. So, and that is true. So we are stippling below. So now I can tell of these two constraints, I have an overlap in this region here. So now I need to do my last line, which is the R plus S greater than or equal to 70. Now in this case here, we can either isolate a variable and use slope-intercept form, or we could find the intercepts of each one. And that might be the easier way to do this, because of the fact that our grid is going up by 5. So if I want to find the R intercept, I'm going to let S equal 0. So I'm going to have R plus 0 greater than or equal to 70. So R is greater than or equal to 70. So my intercept is at 70 on the R. So 50, 60, 70. So here is my point for the R. Then if I want to find the S intercept, I'm going to let R equal 0. So again, I will have 0 plus S greater than or equal to 70, so S greater than or equal to 70. So our intercept is at 70. Now because this is going to be an oblique line, I will join them with the understanding that we are only using the whole values. So now I need to determine whether or not I am shading above or below this region. Use a test point, 0, 0. If I substitute 0 in for both the R and the S, is 0 greater than or equal to 70? The answer is no. So I'm shading above. Now the overlap for the above would be in these points. So here is our feasible region. What we now need to do is we need to determine our corners or our vertices of this feasible region. So it's a triangular shape. So we have 3 vertices. This one is at 60, 40. This one here is at 60, 10. And this one is at 30, 40. So those are the 3 possible places that we will have a maximum or minimum value. So now we substitute those into our objective function, into our cost equation, and we see what kind of values we come up with. So if we start with the first one of 60, 10. Now keeping in mind 60 is your S. So we'll have C equals 12 times 60 plus 8 times 10. And we will end up with 720 plus 80, which is $800. All right, let's try our next one of 60, 40. So we will have 12 times 60 plus 8 times 40. We will end up with 720 plus 320, which is 1,040. by our third vertice, which was 30, 40. So we'll have 12 times 30 plus 8 times 40, which is 360 plus 320, which is $680. So we can now say if you wanted to minimize your cost, so minimize the cost, you would spend $680, that was the lowest of the three, and you would do that by making 30 sport utility and 40 racing cars. If you wanted to maximize costs, you would spend $1,040, and you would do this by making 60 sport utility and 40 racing cars. So we have now found the combinations to maximize and minimize the costs. All right, let's try another example. L&G Construction is competing for a contract to build a fence. The fence will be no longer than 50 yards and will consist of narrow boards that are 6 inches wide and wide boards that are 8 inches wide. There must be no fewer than 100 wide boards and no more than 80 narrow boards. The narrow boards cost $3.56 and the wide boards cost $4.36. Determine the maximum and minimum costs for lumber to build the fence. So just like in our last example, first of all, what we need to do is identify the variables that we're going to work with. So let's let N represent our narrow boards, and W can represent our wide boards. So what are our restrictions? Again, you need to ask yourself, are these whole numbers? Are these integers? Are these real numbers? Well, we're talking about the number of boards. So we can't have a negative amount. We can't have a decimal amount. So we are dealing with whole numbers. We could have zeros. So we've got that they are elements of whole numbers. Now we need to look at our constraints. What else does it tell us about the amount of wide boards? It says no fewer than 100 wide boards. So we need to set that up, and it's the wide boards have to be larger or equal to 100. You can have 100, but you must have 100 or more. And then it says no more than 80 narrow. So that means our narrow boards has to be less than or equal to 80. It tells us that the fence is no longer than 50 yards and it's made of 6-inch narrow and 8-inch wide. So what we have to do is we have to set this one up. So we will have each narrow board is 6 inches. So 6 inches per narrow board plus 8 inches per wide board. This has to be less than or equal to 50 yards. Now because the 6 and the 8 were given to us in inches and the 50 is given to us in yards, we need to convert that to inches. And there are 36 inches in 1 yard. So we are going to multiply 50 by 36. So what we actually end up with is 6 narrow plus 8 wide less than or equal to 1,800. So now we have all of our constraints. These are the inequalities that we are going to have to graph. The other thing is, because they were whole numbers, we should have thrown in here that they need to be greater than or equal to 0 as well. That just keeps us in that first quadrant. So now what we need to do is we need to find our objective function, and that is going to be cost. So C is the cost to do this. And we know that it is $3.56 per narrow board and $4.36 per wide board. So there's our cost, or our objective function that we want to maximize and minimize. So now we can graph. Again, you need to choose which variable you're going to put on which axes. So we'll put the narrow ones on the x and the wide ones on the y. And again, it wouldn't really matter what you chose to do. So now, if we want to graph the number of narrow, so n has to be less than or equal to 80. I'm going to go up here by 20s each time. And so 80, we have our stippled line at this point here. We need to determine if we would be stippling to the left or to the right. N is less than or equal to 80. So we need to have, if we substitute 0 in, 0 is less than 80. So therefore we are stippling to the left. Where, we're not too sure, so I'll just mark some points on the left of the red. Now we need to look at the wide. The wide has to be larger or equal to 100. So again, if I'm going up by 20s, we are looking at the 100. We have our stippled line. Now we want W to be larger than this. So we should know that we're going to be graphing above, but if you were not sure, you'd substitute 0 in. 0 is not greater than 100, so you do not shade where 0, 0 is. So the opposite region is above. So at this point, here's where we have some overlap, and it could go all the way up here. Now we need to draw our graph of 6n plus 8w less than or equal to 1800. And again, it may be easiest to use the intercept method. So if I want to find the n-intercept, I'm going to let w equal 0. So I'm going to have 6n plus 8 times 0 will go equals 1800. So I'm going to have 6n equals 1800. So n equals 300. So on the ends here, we need to go over to 300. And we put our point. And now we repeat the process to find our w-intercept. So we let n equal 0. So we'll have 6 times 0 plus 8w equals 1800. So w equals 225. 6180, 200 is right here. 220. 240. So 225 is right in about here. And we join our intercepts. So now what we need to do is determine whether we're going to shade above or below this region. So again, we can substitute a test point into our inequality. So if we put zeros in, we will have 6 times 0 plus 8 times 0 less than or equal to 1800. 0 is less than or equal to 1800, so I know I need to go below my line. So my overlap is going to be above the blue line, to the left of the red, and underneath the black. Here is my feasible region. So I need to look for my corners. I've got a corner over here. I've got a corner right here, and right here. And those points are at 80 and 100, 80 and approximately 165, 0 and 225, and 0 and 100. So I have 4 corners that I need to check my costs for. So I go over to my cost function, and if I start with 0 and 100, keeping in mind that the x value is your n, that's your narrow axis. So I'm going to have 3.56 times 0 plus 4.36 times 100, and I will get $436. Next, we can try 0 and 225. So I'm going to have a cost of 356 times 0 plus 436 times 225, and I'm going to get a value of $981. Now I can try my corner, that is at 80 and 100, and I'm going to get a cost of $3.56 times 80 plus $4.36 times 100, and I will get a value of $720.80. And then I'm going to check my last one at 80 and 165. So I'm going to have a cost of 356 times 80 plus 436 times 100. I add those up and I get $1,004.20. So you're looking for your maximum and your minimum. Here's our minimum, and our maximum is right here. So what we can now say is that the minimum cost would be $436, and that will occur when you use 0 narrow boards and 100 wide boards. And your maximum cost will occur, and it will be $1,004.20, and that will occur when you use 80 narrow boards and 165 wide boards. So you are now able to tell the company what their maximum and minimum costs would be to build this fence. So, the key idea: to solve an optimization problem, you use linear programming. Begin by creating algebraic and graphical models of the problem. Then use the objective function to determine which vertex of the feasible region results in the optimal solution. So here are your steps. Step 1, create your algebraic model that includes a defining statement of the variables, the restrictions on the variables, so are they whole numbers, real numbers, integers, a system of linear inequalities that describes the constraints, and an objective function that shows how the variables are related. Step 2 would be to graph the system of inequalities and determine the coordinates of the vertices of the feasible region. Step 3 would be to use the vertices and evaluate the objective function. Step 4 would be compare the results and choose the desired solution. And step 5 would be to verify that the solution satisfies the constraints of the problem.